about this padding oracle attack. Here it is, and for this you just need Python, and you just need it in immediate mode. So here's the principle of it. We're going to encrypt 3 blocks of plain text, 48 bytes here, and the first block is XORed with an initialization vector that is 128 bits to match the block size. 16 times 8, 128 bits. All right, it XORs with the IV, then it goes through encryption with the key, and that creates ciphertext. The ciphertext of the first block is used as the IV for the next one, XORed with the plain text, encrypted with the key, and that's how cipher block chaining works. So here's the encryption, but if you were to encrypt only 47 bytes, you'd have an extra byte here that's not determined, and so padding is added. A byte of padding is added at the end. All right, now, when you decrypt, you've got the ciphertext here, and you're going to decrypt it in this 47 bytes of plain text plus padding. And so you decrypt it, you feed in the initialization vector, which is not secret. You take your ciphertext, decrypt it with the key, XOR it, and then you take the ciphertext here is used as the IV here. And this is the weakness. This ciphertext is known to the attacker who doesn't have the key, but they have access to the ciphertext, like they're sniffing on the wire. You know this, and it's XORed here with a very simple operation. So you can control this. And the problem is the padding scheme is easily predictable. And here's the padding. If you have 1 byte to pad, you pad it with a 0-1. If you have 2 bytes, you pad it with 0202. If you have 3 bytes, you pad it with 0303. If you need 16 bytes of padding, if you have no bytes of padding, you add a whole 16 bytes of 16 in every byte. So that way, when you want to remove the padding, you just take the last byte and remove that many bytes, and therefore you can always recover it. So what we do is modify this byte here, 31, and then let it get decrypted. If we modify it, this whole block will turn into garbage, but this 1 byte here will change, and that's the padding byte. So there are only 2 values that will not create a padding error. One is the original value, which will create the original message, and this other value is the one that creates a 0-1 here. So if you can quickly find out what other value does not create an error if the algorithm leaks out the information of whether there was a padding error, and a lot of them do. That's the padding oracle. That error message that tells you if it was the padding error or some other error is enough to leak out information that enables you to forge data without knowing the key. So let's set initial values here. Run Python 3. Whoa, all right, I'm surprised capital letters worked anyway. All right, and then AES is not defined from crypto, that's because I didn't get the F. All right, let me try copying this more carefully. See if I can get all of it. All right. There we go. All right, so now I've defined it. Okay, and it looks to me like I can scrunch this down a little. All right, so now I'm going to encrypt it and print the encrypted stuff in hex because it'll be unreadable. All right, so there's my encrypted hexadecimal hello from AES. Now I can decrypt it here. And as you see, it does decrypt. I'm using AES mode CBC, of course, and I used a key like that and an IV like that, so not particularly random or anything, but the point is anything will do as long as it's 16 bytes long. So here's the decrypted stuff in hex. This is the ASCII, HELLO, and so on. All right, so now we're going to do padding and chaining. So there's a sentence that's 47 bytes long. All right, and so I'm going to pad the sentence by adding a byte of 1 to the end, which is the correct padding, and then I'm going to make a modified ciphertext string where it gets changed to 255. So there. Notice here, now here I take the ciphertext, the original ciphertext, And here's the ciphertext with 1 byte changed. I've changed the 32 byte to 255. So if I compare these, they should be identical up to a certain point. These are the ciphertext. There should be only 1 byte different. It'll be 32 bytes in. And I put an FF in the bottom. So there it is. There's the FF. It used to be a 5C, but now it's an FF. This is the modification where I changed just 1 carefully chosen byte of the ciphertext. Now I'm going to decrypt them both. Okay, here's the decryption. So it's exactly the 5470C. It's going to be different somewhere around here. Here we go. 65, 63, okay. There. The 74, up to the 74, they match. Then the next 16 bytes should be completely destroyed. This is readable ASCII. This is random junk because I changed a byte. Then it's going to start matching again. Here, 66. This is the 3rd byte, which is all intact except for the last byte, which is different. So that's the effect I was describing here. I've changed 1 byte, totally destroying 16 bytes here and changing only 1 byte there. So all these bytes that are in green remain unchanged from changing that 1 byte. And that's the pattern, which this is a lot like what I've said about differential cipher analysis, cryptanalysis. You make a small change in the input and the output in a good cipher, a strong cipher, any change in the input would just scramble everything. But that's not what happens. It has a small localized effect you can measure, and therefore you can attack that weak point and crack information about the key without having to crack the whole key. So, all right. And so that's the game here. All right, only those bytes changed, is what I just showed you. All right, so now we're going to make a vulnerable function. So I am going to make a padding oracle function like a lot of things were. So this is going to be it. I have to save it as pador.py. So let me get out of here. And we move to a directory. All right. Yeah. Do I have pador? I probably do. I do. All right. That's probably already in there. There's already in there, pador.py. So you put it here. You can make your own Python script. You can just import it right from that directory, as long as you're working in that directory. So it's already there. All right, and so now I can import it. Okay, so I'm going to import encrypt and decrypt functions. And I'm going to feed it 47 bytes and encrypt it. Okay. So now I encrypt it. Now I'm encrypting it. This is the way it is when you're attacking a system. It has encryption and decryption, and you don't know the key. All you have is the ability to encrypt things. So here it is encrypting that sentence. All right, then I'm going to decrypt it using the decrypt function that comes. And there it is decrypted. It decrypted into this, and notice it added a 1 to the end. So the decryption function here is kind of sloppy. It doesn't strip off the padding. You can see it, but it is valid padding there. All right, now we're going to observe the padding oracle vulnerability. I'm going to make a modified ciphertext where I change the last byte to 65 instead of whatever it was. And now when I decrypt it, it's going to tell me padding error, which is the oracle. Instead of just telling me failure, it tells me the problem is padding error. So the goal here, we're going to create a valid encrypted message including the word win without knowing the key or the IV. And here's how we do it. We're trying to determine this intermediate state here. So we change this 1 byte here until we get no more padding error. Then we know that this is a 1. So I have to say 1 XOR that, and we'll have this intermediate value. So we can deduce this 1 byte of this intermediate value. And knowing that, we can then deduce the next one and the next one. We can eventually deduce this entire intermediate value. And then we can choose ciphertext that will decrypt into anything we want. That's how it works, without knowing the key or the initialization vector. That's the weakness. So that's the game. So first we're going to get a valid ciphertext. So we're going to just encrypt. This sentence clearly says, I'm a loser. And I spelled things wrong to make the length right. So There we go. All right, so there is my original ciphertext. This is valid ciphertext. Now I'm going to perform 5 modifications of it. I'm going to take the original, I take the first 31 bytes to the original, then I add a byte I've modified, then I put the more of the original there. This is changing byte number 32. So I do this, and so all of them have padding errors, as you would expect. There's 256 possible values, and most of them are going to be padding errors. So what I do is I try all 256, and then I find the one that doesn't say padding error with a loop instead of having to read through 256. So this will try them all, and there's the 2 values. 147 and 154 both do not have padding errors. All right, one of them is the original byte, and one is the byte that turns into 1. So to see the original byte, you can just print out the original byte at location 31. So the original byte was 154. So 147 is the other one that has correct padding, therefore it's the one that decrypted to 1, 0, 1. So now I can fill 16 to 31 with A's and test all 256 values. I forget why I'm filling it with A's, but it doesn't really matter. I could put anything there. Yeah, I put 15 A's here, and then I put anything I want at the end. It doesn't really matter whether I change this or not. Remember, that's the middle thing, and I'm going to stomp it. But if I fill it with random junk, then this will all be random, and this will all be random junk, and it'll still be correctly padded, though, when I have a 0, 1 there. So it's one way to do it. I don't really know why I had to fill it with A's, but it doesn't hurt anything. So that's going to give us intermediate 45. So, all right. So I'm going to fill this with A's, and I should, all right. Oh, because I know what the A is, all right. There, so 147 is correctly padded. So it's, this worked because it creates a random bytes of clear text, and it ends unless the padding is 1. So now I'm going to fill it with B's. And again, I get 147. You can fill it with anything you want, and the attack will work. You can put anything you want in those 16 bytes. So the correct number is 147. So all I have to do is take 147 XORed with 1 to find this intermediate value. So that's going to be 146, 147 XOR 1. So that value there is 146. And now that I know that, I can continue. Now I can change this byte until I get the next one, and so I can slowly get these bytes, and then I can craft a message that will decrypt anything I want. So that's the game. That's how it works. This is the manual calculation. And so if you go through this, you'll find a flag here by just following the steps, and that's fine. And if you want to be tough, you can try the 50-point challenge. And the 50-point challenge is this. I give you a different PADOR PyX file to take and save it in your downloads folder. It then decrypts the string, and now you have to attack it. And you need to, so if you feed in this thing, let's see if I can do this. PADOR chal2, I'm going to try this. Let me download this thing. Save linked content as, okay. I'm going to go to SAM 141, PADOR, okay. Now I'm going to put it in there, PADOR chal2.py. Looks like I have already put it in there. All right, good. So I should be able to run this. All right, let's try this. All right, that decrypts. All right. First one should say error, no name included. Huh, that's interesting. Looks like I put a correct solution here by accident. That's interesting. Doesn't really matter. And this one here, second one should be a padding error. All right. This may be a problem. I have to move PYX to PY, Python 3. Well, this may foul up my beautiful challenge. However, I'm not sure it will. That was just to show you how to do it. The point is here, it's going to go to my server where you can't see the code. And so you're going to have to, if you put in ciphertext like this, it's going to tell you, this one worked. Okay, I'm going to have to work on this. I did it right before class and it worked. Okay, I thought I had this fixed because I was able to get in, but now it's accepting everything, so I'm going to have to work on it again. I'll let you know. Maybe I'll get it working by next week. Now it seems to let everybody in with invalid data. All right. Before it rejected everything, now it accepts everything. I still haven't got it fixed. So nah. But I'll have to work on it. All right. Anyway, I'm going to stop recording.